right, so we're gonna work toward a stoichiometry problem, but in order to hit a stoichiometry problem, there really are some foundational skills, and I want to work through these because if there's a gap in understanding, rather than just struggling with calculations, I can help. So we're gonna balance, then we're going to calculate molar masses, then we're gonna do something with that molar mass, then we'll make sure you can do a percent yield, and then we'll talk briefly about molarity, which is just a fancy way of saying concentration. And if you've got those down, stoichiometry will be no problem. So how has balancing been for you?
I think balancing is one of the things I understand the most.
Okay, excellent. So let's balance this one and then we'll move on with this. So on this one, we got P4. What does that parentheses S mean?
Oh, that it's a solid.
Very nice. And that only comes up when you're asked, like, how many moles of gas will you make? And you have to, like, actually know which of these count as moles of gas. So it looks like here we are mixing phosphorus and chlorine. Oh, gosh, that's going to be horrible. They both smell terrible. And making what I'm guessing is phosphorus chloride, although I've never heard this chemical pronounced. And it turns out it's a liquid, L. These are all lowercase letters.
Okay.
So solid, gas, liquid, and then of course if you say AQ, aqueous. So, all right, talk me through this. How do we balance this?
Well, first you write all of them out. So P, which is 4.
Okay, we see 4 of those.
And then CL, which is 2. And you do the same for the other side.
Okay.
So P is just 3, because that's where I get stuck.
Okay.
Like,
So when we have these subscripts, they only apply to the thing directly in front of it.
right.
The thing that would apply to everything would be as if we wrote a number out here.
Okay, so then it's just 1,
Good. 1 phosphorus and then
3.
3 chlorine. Very nice. Okay, this is going to be interesting to balance. What do you want to do first?
Maybe try to get P to 4.
I think that's a good idea. When I balance things, I always just do whatever seems easiest first.
Mm-hmm.
So, all right, how do we get 4 phosphorus on this side so we're not destroying matter?
Add 4 on this.
All right, very nice. We're going to put a 4 right there in the front. And that means that we now have 4 phosphorus and how many chlorine?
3
So 4 times 3.
is 12.
Very nice. And we love calculators. We'll never stop using calculators for this. Okay, so it looks like our phosphorus is all set. What's next?
I have to get chlorine to 12.
Okay, what are you thinking?
Multiply by 6.
Okay, so we're going to put a 6 up here. Now that 6 is only going to apply to the chlorine because it's right after it. So I'm going to do that. 6 times 2 is 12. We've got 4 phosphorus. We've got 12 chlorine. I call that beautifully balanced. Okay, and don't forget, when we don't see phosphorus there, we put a 1 there. The reason you shouldn't write it because it's not considered professional, but keep it in mind because later when they ask you about moles and mole ratios, this is 1 mole, 6 moles, and 4 moles. So that having that 1 there kind of reminds you, like if I start with 1 mole of phosphorus and as much chlorine as I want, how much of this phosphorus chloride am I going to make? Well, I'd make 4 moles. If I start with 6 moles of chlorine and as much phosphorus as I want, how many moles of this am I going to make? Still 4. Okay. If I had 12 moles of this, how many moles of this am I going to make? Yeah, don't overthink it. This is the molar ratios. And that's a big part of stoichiometry. That's kind of the middle part where you're converting moles of one thing to moles of another.
So whenever a question's saying like, and you have blank of however many you want, it's mostly focusing on the other.
Right, right. So if it says you've got this many grams of phosphorus, well, first you're going to convert it to moles. And then it says, how much phosphorus chloride do you make? Well, then we go moles of phosphorus to moles of phosphorus chloride, and then we can go into whatever final unit wants. But anytime we're going between different compounds, we're always going to go back to this, and we're going to try to figure out how to convert moles of one thing to moles of another. All right, well, that was excellent. Shall we check our answer just for the fun of it?
Sure.
Okay, we're going to put, it doesn't even have a 1 because you're not supposed to do it. Wow, that's an incredibly clever way to force you to know chemistry. I'm going to put a 6 there. We're going to put a 4 here. Let's see. Ta-da! Nice job. All right. So our next one, good job getting an eraser. Our next one is going to ask to calculate molar mass. So in the previous question I said, if I had like 10 grams of phosphorus, how many grams of this am I going to make? Well, we would have to go grams of phosphorus to moles of phosphorus, moles of phosphorus to moles of potassium chloride or phosphorus chloride, and then we could go grams of phosphorus chloride.
Okay.
The way you go from grams, let's say 10 grams of P4 to moles of P4 is going to be a molar ratio or a molar mass. So we need to know our molar mass. Okay. So this problem is asking you to calculate the molar mass of silicon iodide. How do you know that that's silicon iodide? Because I'm right. I'm very good at this point. I've been doing this a long time.
How do you know?
How do you know it's silicon iodide? Why isn't it SIL?
Because the last two are lowercase, so it means it goes together with the capital.
Oh, sneaky. Actually, there's only ever 2 letters, so we know these have to go together.
So then the other one's different.
That's right, and that means it has to be uppercase.
Okay.
So this is going to be silicon. I always struggle to write this. There's not another silicon. I don't know if there's another L. Oh, spelling is terrible. No, just silicon. Okay, that's cool. Oh, there we go. I was missing the C. Silicon. And then this, even though it looks like a lowercase l, is just a sans serifed I, so this would be iodine. Okay, and then the subscript 4. What does that 4 mean?
Just for the iodine.
Right, that 4 only applies to the iodine. So what I'm seeing here is 1 of the silicons, and for the iodines, I'm seeing 4. Okay, so what's next?
So then you have to find how much, you have to use your periodic table.
Yeah, we need a periodic table.
Yeah.
So I'm gonna grab one for you and one for me. So, how much does silicon weigh? Well, let's take a look. Got it.
How?
Well,
Actually, yeah.
years and years and years of practice.
Yeah.
Okay, so I
Oh,
found
here it
silicon.
is.
There we go.
Yeah.
Looks like
28.09.
excellent. So 28.09 grams. And then iodine. How much does iodine weigh?
Iodine is 126.90.
0 grams. Okay. And then we're going to type that in the calculator because we wouldn't dream of doing mental math and chemistry.
Grab 507.6
That's for the whole thing?
for the whole thing.
Okay. Well, I'm not quite that quick, so I'm going to double check math for you. So this would be 28.09 grams because 1 times anything is the thing itself. And then down here, we're going to do 4 times 26.90. When I was in school, my dyslexia was so bad I had to do every single math problem twice just to make sure I hadn't like typed something wrong. But it means I got really fast with a calculator, so that's great. Okay, so 535.69 grams of silicon iodide per 1 mole of silicon iodide. So that's what that tells you.
So is it basically the same as how much it weighs per one?
Yes, if we have 1 mole of this garbage, so here's the pile of silicon iodide. If this is exactly 1 mole, I don't even have to weigh it. I know that it automatically weighs 535.69 grams. Automatically. All right, let's type it in. Let's see how good we are. We'll be really upset if we get this wrong. No, we'll just try again. 535.69. That was the same thing you got?
Yes, sir.
Okay. Let's try it. Okay. Got 500. Excellent. We got it right. And let's see. They did it exactly the same way we did.
Yeah.
Excellent. Okay. How are you feeling on molar mass?
I think I'm good.
Good. So let's return to the idea of using that molar mass to convert from grams to moles, because that's what's next up here is the idea of a molar conversion. So in this problem that I wrote for you, 10 grams of P4, how do we convert it to moles of P4?
how to go back to moles?
Yeah, I want to go back to moles. I told you I've got 10 grams of it. How do I go back to moles of it?
Well, then would you take the molar mass?
Yeah, you'd have to figure out the molar mass. So, how much does P4 weigh?
P4.
Well,
Let's see.
yeah, so I see phosphorus weighs 30.97 times 4, so that's 123.88 grams of P4 per 1 mole of P4. And if I do that math, I'll figure out exactly how many moles I actually have of this.
Okay.
And then I can use those molar ratios to convert the moles that I have of the reactant to how many moles I'll get for the product.
Okay.
But let's do the problem that's actually in the practice. So, talk me through it. How would you do this?
So if it's saying that we have 20 grams, then first we're going to find the molar mass.
Good.
And all that.
Oop, I already wrote the wrong letter, so hold on a second. Let's see. All right, that's going to be manganese, I think. Mn, and then in parentheses, ClO3. Okay, and there's 2 there. What does this 3 mean?
The 3 just goes for the oxygen.
Good. And what does the 2 mean?
For the whole thing in the parentheses.
Everything in the parentheses, that's right. So 2 chlorine, and then 3 times 2 oxygen, so 6 of those.
Yeah.
Okay, so always rewrite our given first. And then, as you said, we're going to need the molar mass. So we need to figure out what belongs here.
Right.
So that we have 1 mole of MnClO3. Honestly, that was so bizarre. I just want to look it up. I want to know what to call it.
That's a lot.
Yeah, ClO3. Whoop, O3, 2. Let's see. This is called manganese chlorate. Okay? So, how much does manganese chlorate weigh? 1 gram or 1 mole of it?
You want to find whatever the NN weighs.
Okay.
Which is.
No, we hardly ever. Manganese. Who knows what manganese is?
54.94.
Okay. And how many of those do I have?
We just have 1.
Good. So 1 times. Give me that number one more time.
54.94.
94 grams. All right. What next?
Then the chlorine, which.
Well, first, how many do you have?
Oh, 1. Oh, for the chlorine we have 2.
Very nice. So 2 times. This is one I do a lot, so I've got this one memorized. This one is 35.45.
Yeah.
Okay. How many oxygens?
Oxygen, we have 6 of them.
Correct. And we got that 6 by doing 2 times 3 oxygens.
Yeah.
So, an oxygen.
Is 16.
There we go. I love the nice round number ones, don't you?
Mhm.
Okay. So, this is brutal. Let's go ahead. Yeah, let's calculate them all and add them together. So, I'm going to bring my calculator over here. Oh, this first one's easy.
Yeah.
4.94 grams. Then what do we do once we got them all?
We add them together.
Good, so we're going to add them all together. Ooh, I don't want to do that in my head. Okay, here we go. 96 plus 70.90 plus.
We got the same thing.
You got the same thing? Excellent. So that means that for every mole of manganese chlorate, we have 221.84 grams of manganese chlorate. And I'll tell you, a lot of times students don't understand why I keep writing the same compound over and over as part of the units. But later, when I convert from manganese chlorate to something else, if I haven't been writing the compound all the time, I'll forget what thing I have grams of in my math. So yeah, is it a pain? Absolutely. But it's a habit to get into that'll save you a lot of errors.
We can also use that to make sure that you're going from diagonal from
Yes, exactly. You can make sure you're canceling out grams of the same thing. Okay, so let's do the math.
Fun.
Yep. So we're going to do, talk me through it. What are we going to do?
87.20 times, well, 1, but I mean, this is the same
Right,
thing.
times 1.
Divided by 221.84.
Okay. So, yeah. Okay, so I got 0.39. Is that what you got?
Yes.
All right, let's see. Okay, we got it. Very nice. All right, so those were very basic things. If you can do that, you can do a stoichiometry. There are 2 more things that sometimes come into these stoichiometry problems, and that's percent yield and molarity. That's right. Excuse me. Wait for a second. So if we wanted to figure out percent yield is pretty simple. It's always the actual divided by the theoretical. Times 100 equals the percent yield. Okay. The tricky part is when questions ask you to work backward like this. So this question says over here, your theoretical yield was 945 grams, but we know we only got 72.1% of that. So what was the actual yield? So can you talk me through it?
Okay.
Let's plug stuff in.
Yeah.
What do you know?
We know that the theoretical is 945.0 divided by whatever we're going to get.
Okay.
And then times 100 equals 72.1.
That's right. Okay. And so the thing we're wondering about is this right here, the actual. Okay. Well, this is just algebra. So we're gonna get rid of the question mark and put an X there. We're gonna parentheses around this, and now this looks like any other algebra problem. So what would you do? Well, it's already multiplied on this side, so we're gonna divide both sides by 100. Okay, so then we're going to get x over 945 is equal to 0.721. Now what?
And then we have that one. So then we're just left with 940. We haven't gotten rid of that yet.
We haven't gotten rid of that yet. Very nice. I actually struggle these days to help students with math because like the way that you're taught to make it look on your paper is so different from the way that I was taught to make it look sometimes. Every now and then I show somebody something and I'm like, I don't know what you're doing. And honestly, it's fair, and ironically my mom and I had the same issues when I was in math. So
I mean, with these I would just struggle to figure out what do I do first. But once I figure out
right.
first.
Well, and we're getting there on that one. So looks like the theoretical or the actual yield was 681 grams. Now let's make sure this makes sense.
By plugging it in.
Yeah, we can plug it in and work backwards. We can also just think about it for a second.
Yeah.
Is this less than what we would theoretically get?
Yeah.
And is this less than 100? Okay, then we're set. That's how you check to make sure you haven't mixed up your theoretical and your actual. So 681.3 grams. Let's see. Ta-da! Okay, so that's percent yield. Last one that's worth covering. Yeah, let's talk molarity. I see a lot of students struggle with this, and I think the thing they're missing is the basic. Do you know, so molarity is a word, and if I write the capital letter M, it's the same exact thing. What units goes with that? Okay, listen, it's matching tattoo time. Because it will never change. Yeah. It's literally always moles per liter. Okay? Which means some amount of substance and some amount of volume. It's the exact same thing as concentration. This could easily be moles of sugar per liters of water because we're trying to make a sugar syrup.
Okay.
It could easily be moles of Kool-Aid mix per liter of water because we're trying to make Kool-Aid.
Okay.
But it really is just a concentration.
Mm-hmm.
So moles per liter, moles per liter, moles per liter, moles per liter. That's what this means.
Okay.
All right. So let's work this problem.
Okay.
Another way to think about this is solute, to put some vocab in there, over solvent. And when you mix them, you get the solution.
All right.
All right.
Solvent is 0.0200.
0.0200 moles.
Yes.
Good.
And of Fe, that whole thing.
Yep.
Yeah.
Okay.
And then the volume is a solvent, right?
That's right.
So then it's 0.1028 liters of H2O.
Okay. That's it.
And
Plug it in.
Oh.
Now, I could be mean. I could give you grams instead and you would have to convert to moles.
Okay.
Or I could give you milliliters and you'd have to convert to milliliters. But that's really all I can do. It's just moles over liters. You get it to moles over liters, and after that, it's just, can you plug it in the calculator?
Sorry, this is a dumb question. Milliliters is 1,000 liters.
1,000 liters. But I will also give you that conversion if you need it. I'm not trying to trip people up on a table they may or may not have memorized. In college, absolutely you should have it memorized.
Yeah.
Right now, So I got 0.19 when I did this divided by this. 19, I'm rounding that to 5. Is that what you got?
Yes.
Okay, that's it. That's the molarity.
Okay.
Okay, moles per liter, moles per liter, moles per liter. Okay, those are the skills you need to do stoichiometry. So let's put them all together and do a stoichiometry problem. So this problem says if 4.46 grams of hydrogen bromide are reacted with 12.6 grams of KOH, how many grams of KBr will be produced? All right, what's our first step?
Balance.
Absolutely, we gotta balance first. If you haven't balanced your reaction, your math will end up, almost certainly it'll be wrong.
Okay. So then 2 inches.
All right. How many hydrogens did you say?
2.
Very nice, good catch. There's one here and one here. How many bromine?
1.
Okay. How many potassium? How many oxygen?
1.
All right, how about the other side?
There's 2
Mhm.
hydrogens.
Mhm.
There is 1 bromine.
Mhm.
There is 1 K.
Mhm.
And then there's 1 oxygen.
Oh my gosh, thank goodness. What did we just learn?
Out of balance.
It's already balanced. Look,
Yeah.
we don't have any more
We don't
work to
need
do.
to do
Oh, wonderful. Okay, so that means when it's time to convert moles to moles, they're all going to be 1-to-1 ratios.
Okay.
Okay, I'll be honest with you. I'm going to skip this problem because we need to see one where that's not true. So here we go. This is ugly. Let's do this. This is fabulous.
Okay.
All right, let me find an empty spot on the page. I don't actually know what SB is. Yeah, that's significantly less fun. The good news is it's great practice.
Yeah.
All right, I'm looking for SB up there.
SB.
Oh, I remember why I didn't remember what this was. Because the name of SB is antimony.
Oh. Where do we
Probably Latin, if I had to guess.
Yeah.
Okay, so SB and O. And if you're watching this later, pause it. Let's balance this. All right, talk me through it.
We have 1 SB
Okay.
and 2 O's.
Okay, 2 oxygen. What do you see on the other side?
We have 4 SB and 6 oxygen.
Okay. What do you want to do?
Maybe get the oxygen to first.
Okay. How do you do?
By doing 3.
Good. We need a coefficient of 3 in front of this oxygen. That makes 6.
And then we do SB34, so we can just change the coefficient to 4.
Very nice. All right, that's one of those that looks intense when you look at it, and then you just never know how easy the balancing will be. Just as a point of that, this was already balanced, and this one took us 2 steps. Okay, so now let's read the problem, now that we've balanced it. 53.1 grams of SB, and when I talk my way through these problems, I like to point. Sorry, I'm being distracted by the fact that I've spilled my water all over the table. That's okay. So I like to point to where in the chemical reaction I'm actually talking about. So 53.1 grams of SB, that's a reactant, are reacted, and 0.0785 moles of SB406 are produced.
Okay.
What is the percent yield of this reaction? All right, that's a little spicy.
Okay.
So let's get rid of some information first. Let's get rid of everything after the 53.1 grams of SB are reacted.
Okay.
If I said 53.1 grams of SP are reacted, how many grams of this are made? Would you know how to do that? All right, talk me through it.
So to get, these are all moles, so we need to get from moles to grams, right?
One of them is not gram. Oh, these are all moles.
Those
Yes,
are all
these, the coefficients are always moles.
So do you have to, if it's already giving you this in grams, you can just leave SB, right? And we're only trying to figure out how many grams are in.
Right, but you can never go grams to grams. You've got to go through moles. Anytime you're going from one compound to another, you have to go through moles. So one of the ways to think about this is moles of A to moles of B. It's the only way to go. But you can go from grams of A or liters of A or particles of A or molarity of A. It doesn't matter. You can pick anything you want. And then at the end, they could ask you for anything you want. They could ask you for grams, for the molarity of it, for the liters, for the particles. But either way, if you're going from one compound to another, you absolutely have to convert it to moles and then use that mole ratio and then go from there. It's a little bit like, this is the old phrase is bottleneck. It's like the point that everybody has to get through.
Okay.
So
we have to get 53.1 grams to moles.
Perfect. Okay. When in doubt, always just convert it to moles. The chances are you're going to need it. Okay. Talk me through it. How are we going to do this?
Is this where you get molar mass from?
Yes, very nice.
So then if it's saying we have to find the molar mass of SB first. So then we look on our periodic table. It says that SB, if I could find it. Have we already done this one?
No, we haven't done this one.
SB is 1 to 1.76. And then we have to multiply that by 4 because
we do not.
But we don't.
That is a coefficient. The only time we multiply things is if they're down here.
Okay.
Okay, if we do that, you'll be working in the molar mass of 4 SBs, and we only want 1. Okay.
So we will only ever multiply if it's okay.
Right, just these subscripts, never the coefficients. Okay.
So then that means it's 121.76 grams per mole.
That's right. This one was actually a little bit easy for us. All we had to do was look it up. We didn't actually have to do, like over here, we're going to have to do 4 of these and 6 of these, etc. Okay. So now you've converted it to moles of SB. What next?
Now we have to figure out if we have 1 mole of SB, then how many moles of the product we'll get.
Right. Very nice. We got to go moles to moles. So moles, we want to go moles of SB to moles of SB406. So you tell me, what's the ratio here? And look up here.
Well, if we have 4 SB, then we'll get 1 of the product.
Wow, nice job. Okay, now I've run out of space on my, oh no, wait, I haven't. Oh, this is so great, I forgot I folded this in half. Okay, so got grams to moles, moles of SB to moles of SB406. Now what?
Now the question's asking for percent yield.
The question's asking for percent yield,
Yeah.
but what does it give you as how many are actually produced?
0.0785
What unit?
moles.
Moles. So if it gave you grams, you would have to convert this to grams. But right now, it's in moles, and the other piece of the puzzle that they gave you was in moles. So let's leave it in moles.
Okay.
All right. How are we going to do this math?
53.1 times 1, which is 53.1, divided by 121.76 divided by 4.
Okay. I got 0.1. Good. And what are my units?
That's moles of SB406.
Very nice. Okay. So that's. Say it again?
We get the percent yield.
Correct. So what is this?
That's the actual. No, that's theoretical.
That's the theoretical. This is the one that we got just based on math.
Right, but then it's saying that the theoretical was 0.075.
Right. Right. So the actual was 0.0785, and the theoretical, what could have happened in a perfect world.
Yeah.
There you go.
Times 100.
That's right. Times 100. Okay, that'll give us our percent yield. What is it?
Oh, I just messed the whole thing up.
That's okay. Just type it in again. If you're watching later, this is your chance.
I got 72.0.
I think that rounds to 0.2. There we go.
Yes.
Percent yield. Okay. Let's take a second to find out. But here's the thing. Even if we get this wrong, we're oh bugger. Hi, here we go. Let's connect this again. Even if we get this wrong, we're not going to be upset because we did like 5 different kinds of math here. We're just going to figure out which one we got wrong and fix it. So, oh, thank goodness we're back. All right, let's type in 72. 72. And I think this will always give you it correctly as long as you are within 2% or something. So let's show the correct answer. We could have been doing this all. Hey, 72, very nice. Would you like to try another?
Sure.
Okay. You tell me. I can keep doing these problems basically until 5 o'clock, but when you want to be done,
No, yeah,
we'll be done.
I think I always freeze whenever I first look at the problem.
Yeah, so I'll tell you what, the next one, I won't say a word. You talk me through it. How do you want to do this?
Oh, fun. Well, first you can just balance it.
Great. Always balance first.
So,
Talk me through it. How do you want to balance this?
if we have one AL.
There we go.
Yeah. So that's 1. And then we have 2 hydrogens.
Okay, my people working along at home. Pause, balance. You're not getting out of this.
So we have 1 AL. And
Wow, it's not gonna. That's so obnoxious. It's okay. I recently figured out how to fix this.
There you go.
I know. Feels a little analog, which is kind of fun. Okay. How many aluminum do you see?
1.
Okay, and on the other side?
We have 2.
Okay. How many hydrogen do you see?
2.
Actually, wait, I said you would talk me through it. You keep talking me through it.
We have 2 hydrogen. We have 2 hydrogen on the other side as well.
Okay.
And then for the S, we only have 1 on this side.
Okay.
And then on the other side, we have 3.
Very nice, because that 3 applies to everything on the inside there.
And then we have 4 on this side. And then
Oxygen.
on the other side, we have 12.
Good.
Fun.
Yeah. All right, what do you want to do first?
We can get the oxygen to 12
Okay, let's do it.
first. So, well, then I was going to change. I guess that's fine.
Balancing is going to be frustrating regardless. Just strike out, try something, and if it absolutely sucks, start over.
Okay.
So what do you want to start with?
Let's just start with the oxygen.
Okay.
So if we want to get from 4 to 12, we
Okay.
have to multiply by 3.
Good.
Yeah.
So where are you going to put that 3?
We're going to put the 3 in front of the whole thing.
Very nice. It belongs here.
So that means that all of it's going to change.
Correct. And we're so excited.
Oh, yeah. So now we have 12 oxygen.
Okay.
But then we're also going to have 12 of, no, not 12, 3.
Good catch.
Yeah.
3 sulfur.
And then hydrogen, we're going to have 6.
Okay.
So now we got sulfur to 3 too, which is on the other side.
Okay, that's
and
great.
Now we need to get hydrogen on the other side to 6.
That's going to be pretty easy to do.
Yeah.
But look at what else you have to do.
We still have to do O.
Oh, wait. Yeah, this is going to be great. Oh my gosh, I was making it so much harder in my head. Okay, go ahead. Talk me through it.
So we could just do, is it fine to do the hydrogen next, or should we do
Sure, you can do it in whatever order you want.
Okay, well then we can get the other side from a 2 to a 6 by making that a 3.
Okay, we get 3 hydrogen, that's
So now
6.
And then lastly, gotta get aluminum from 2. On the other side it's 1, so we need to add a 2 in front of the other side.
There we go.
And make that 2, so now it's all the same.
Ta-da! That's a beautiful piece of balancing right there. Very well done. Okay.
So
Now that you've done this, talk me through the problem, and I will point to what you're talking about here as you talk me through it.
So we have 5.5 moles of aluminum 2SO4 are produced. So 450 grams of aluminum were reacted. What is the percent yield of this reaction?
Okay.
Okay.
What are you thinking?
Well, it's giving you aluminum. We have to go from moles to moles.
Right.
So then do we have to change the 450 grams to moles?
Very nice. They gave us 450 grams of aluminum, but if we're trying to go from aluminum to aluminum sulfate, we're going to have to go moles to moles.
Okay.
So if they give us grams, we're going to have to go grams to moles to moles.
Back to grams? Or
Nope,
no, just leave it?
because the problem gave us moles here.
Oh, yeah.
So
you
we
just
can
want
stay
them-
there.
You
Okay.
just want them to be the same, or does it always have to be both of them or moles? Or can it be both of them grams to get it?
It can be any of those, but for percent yield,
Oh,
you've got to do moles divided by moles or grams divided by grams. They have to be the same
So
unit.
they just have to be the same, yeah.
So talk me through the math. What are you thinking?
So we have 450 grams of aluminum.
Okay.
And then when I get it to moles, you have to find the molar mass of aluminum.
Mm-hmm.
So if how much does aluminum weigh?
I genuinely don't remember. That's not one I use a lot.
26.98.
Okay, where will I put that?
Well, we have to multiply that by 2, right?
No, you don't.
Oh, right, because it's not the. Okay,
There you go.
Yeah, so you just leave it, so you put it on the bottom.
Right. If there was a 2 down here,
Mhm.
yes.
Right.
But since there isn't, that's right.
You just
So,
leave it.
what'd you say it was?
26.98 grams. Moles,
Good.
Grams, yeah, grams.
And then what goes on top?
For 1 mole.
Good.
Per 1 mole of aluminum.
Wow, so professional.
So now you want to figure out how many moles of aluminum are in 5.5 moles of the product.
You can, but remember, we're still in conversion mode.
Okay.
If you're trying to convert aluminum to aluminum sulfate,
Yeah.
how do you make that conversion? Because you're right, we want to end up with moles of aluminum sulfate. So how are you going to convert?
Well, there's 2 aluminum equals 1.
That's right.
Yeah.
Good. There's always an invisible 1 there.
Mhm.
So how do I do the math down here to make that work?
So then you do 2 moles on the bottom of aluminum over 1 mole of the product. I'm just gonna say the product.
The product.
Yeah.
It sounds very professional. Play to your strengths.
Yep.
Okay. So let's check our units here. Grams of aluminum, grams of aluminum, moles of aluminum, moles of aluminum, and this leaves you with moles of aluminum sulfate.
Right.
I agree that you want moles of aluminum sulfate, but tell me why you want it.
Because why we want moles?
Yeah, why are you trying to get to moles of aluminum sulfate?
Because that was the
Yeah.
Because if you have a certain amount, if we have a certain amount of grams of aluminum, we want to know how much of the product will make.
Okay, and why do you want to know that?
Because we want to find the percent yield.
Very nice. Okay, so we're about to do this calculation. What is this going to give us, actual or theoretical?
That's going to give us the theoretical.
Right. Okay. The only way to get the actual is to measure it, but the theoretical we can always do on paper. So, talk me through it.
450 times 1 times 1 is 450.
Good.
Divided by 26.98 divided by 2
okay.
is 8.33. I mean, I guess you could round it to 4. 8.34.
Good.
Moles. So that's the theoretical. But then you have to divide 5.5 by
Very nice.
8.34 times 100.
One of the fun things of making these videos is that I'm always wondering, like, are we making a mistake right now? Like, I might not know, but the person watching might, and they're just, like, watching it unfold. Yeah.
So I got 65.95.
That's what I got, 65.95% yield.
Mm-hmm.
All right, let's see. Hey, very nice. Very nice. Now, you'll notice this says 65, but our answer actually rounds to 66.
Yeah.
That's probably a difference in what we're using as the molar mass for aluminum. The periodic table we're using might be a little bit out of date. It could also be how we round it.
Okay.
But this is never going to be a problem.
Okay.
So, how you feeling? Do you want one more?
Maybe one more.
All right, let me look through these and see if I can find you a mean one.
All right.
Oh, this is a great one. This is a different kind of problem.
Okay. Okay. If 0.2747 moles of are reacted with how many grams will be produced? Okay. Well, first you want to balance. Sure
it's so nice to start confidently. Okay, talk me through it. How are we balancing this?
First, we have on the reactant side, we have
1 phosphorus.
but we have 2 chlorine.
Okay, promising.
And then on the other side, we have 1 phosphorus, but we have 3.
Heartbreak.
Yep, we were so close.
So close. All right, so what am I going to do?
We can get this side to 6 and then this
Hey,
to 6.
very nice. That's right. Anytime you've got something that looks like, oh my gosh, I've got to multiply by 1.5. Probably not. So how would I do that?
We would do 3 in the front on this side, which would get it to 6. And then on the other side, we can do 2.
Okay, so that makes the chlorine 6. And this side, we're going to put a 2.
But that's also going to change the phosphorus.
Correct. So how many phosphorus?
Now we have 2 phosphorus, but we can just change the other side and make it a 2.
Ta-da! Okay, beautiful.
Now it's balanced.
Oh gosh, incredible. Love a balanced equation. Okay. All right, what's next?
Now it's giving us 2 moles, but we want to get it to grams.
Okay, why do you want to get it to grams?
Because it's asking how many grams of the product we want.
So let's talk through which thing we're talking about.
Yeah.
Okay, so talk through the problem and I'll point.
Okay, so we have 0.2747 moles of chlorine, and it's reacting with 0.06202 moles of phosphorus, and now it's asking how many grams of the product.
Right. Why do you think they gave us the amount for both of the reactants?
Because we're going to have to get both of them to grams.
We're going to have to convert both of them from moles of the reactant to moles of the product, and then moles of the product to grams of the product.
Fun.
And we're going to have to do it for both of them. What are we going to do once we get the answers for both of them? What if they're not the same? Let's find out.
Okay.
Let's just try it.
Okay. So we have 0.2747 moles of chlorine. And to get that to grams, we have to find the molar mass.
Whoa. Do we want grams of chlorine?
We want, I don't know, what do we want?
Read the problem again.
If we have those moles, we're trying to get grams of the, okay, so then we already know that you need 3 of the chlorine to have 2 of the, oh brother, okay.
So that right there is why you have to be careful of not saying the material you're talking about, because you'll trick yourself out of it. So even if you have to make up names, and this is Bob, Steve, and Lynette, like I don't care what names you pick, but like make sure you're talking about the thing you're thinking about.
Okay. So now we have that, but we're trying to find grams, so then do we have to change?
Grams of what? Grams of Messiah?
No.
Okay.
Grams of
PCl3, yes, good. Okay, so how am I going to do that?
Well, this is 2, but we want 1.
Right.
So do we put 1 on the bottom?
Oh, you already did moles.
Oh, right. Okay.
So you've done moles of chlorine to moles of phosphorus chloride.
Yeah, but then we want to get that to grams.
Okay. How do I go moles to grams? Right.
Yeah.
Oh, you already said this and I cut you off. I apologize.
No.
You're right. 1 mole of PCl3. I apologize.
No.
1 mole of that. What do I put up here? Yeah.
Yeah. Okay.
All right, so let's figure out how much does this weigh.
So phosphorus weighs 30.9, what is it, 97.
Okay.
And then chlorine is 35.45, but now we multiply it by 3.
Right, we've only got 1 of the phosphorus, but we've got 3 of the chlorine. So we're gonna add, or we're gonna multiply those.
And add it to 30. Okay, I got 137.32.
And I got the same. Okay. Beautiful. 32 grams per 1 mole of PCl3. When I was in school, if we said PCl3, we would get in so much trouble. We had to say phosphorus chloride. But here's the thing, I don't even know if phosphorus chloride is the right name. I don't teach the naming anymore. I probably should. It just feels like a week of your life you'll never get back. And if you decide to be a chemist, you'll learn how to do the names. But okay, so what now?
Now it's ask. Wait, what was the question? How many grams we produce? Oh, we have to do it all over again?
Correct. But this time, we're going to do it differently. How are we going to do it this time?
We're going to use phosphorus instead of chlorine.
Very nice.
So we have 0.06202 moles of phosphorus. And the equation says that if we have 2 moles of phosphorus, then we'll have 2 moles of PCl3.
Okay. Now, could this just be a 1-to-1 ratio?
Yeah.
And could we just then have skipped it?
Yeah.
Here's the thing, mathematically, yes, but as far as communicating with chemistry, no.
No.
So writing this is important. This is telling your audience, I'm converting moles into this product, PCl3. Okay, so nicely done.
And then we take that and we do the same we did with the other, which was if we have 1 mole of PCl3, then we'll have 137.32 grams per mole.
Okay, so we're going to essentially take 2 different routes to figure out how much of this product we're going to make.
Okay.
So, shall we do the math?
Sure.
You want to do the top one and I'll do the bottom one?
Okay.
Okay. Okay. I'm doing mine twice to check my math because yikes. Okay, I got 8.5 0.52 grams.
And I got 25.15 grams.
25 point what?
15.
15 grams. Okay, so depending on which thing we do our math with, we get different numbers. So you tell me, how many grams are we actually going to make?
I don't know.
Well, and this is where it's time to think about this. And once again, when I say time to think about this, it's time to go back to this.
Yeah.
And I like to think about this as recipes again.
Okay.
So I've got this many moles of flour, this many moles of sugar. How many cookies am I going to make?
Yeah.
Well, if I did the math and one of them would make 25 cookies and one of them would make 8, how many cookies am I actually going to make?
8.
Right, because I'm going to run out of the sugar first.
Right. Okay.
Same thing here. We might call it things you've never seen, but if I've only got enough chlorine to make 8 PCl3 cookies, it doesn't matter how much flour I've got. Yay, I could make 25, but only if I had enough chlorine, and I don't. Okay, so you tell me, how many are we going to make?
8.52 grams.
8.52 grams. Very nice. Let's check that answer. Hey, very nice, very nice. So that's called a limiting reactant.
Okay.
What you just did was essentially figured out which of these two reactants was going to limit how much you could make.
So whenever you're asking for a limited reactant, it's whatever is going to run out first.
Correct. It's whatever runs out first, meaning whatever whichever gives you a lower amount of the product.
Okay.
Absolutely beautiful. How are you feeling?
Good, I feel better.
Good. Let me take a quick look at this last one. We won't do it. I just want to talk you through it.
Okay.
Oh, okay. This is the exact same thing. It's another limiting reactant problem.
Yeah.
You would, in this case, go grams of hydrogen to moles of hydrogen to moles of this to grams of this. So this is grams to moles to grams.
Okay.
And then you would do it again for the boron.
Yeah.
Grams of boron. Wait, boron? Am I lying to you? Yeah, grams of boron to moles of boron to whatever we're calling this, Jeremy, and moles of Jeremy to grams of Jeremy. Okay? I genuinely don't care what you call it, just make sure you know what you're talking about.
Yeah.
And then why don't we just take a look at that correct answer? Oh, that means nothing. Let's actually see how they did it, and we'll see if they did it the same way. Okay. Yep, that's exactly what they did.
Okay.
They did the math twice, and they figured out which one of these made less.
Okay.
All right, very nice.
Yeah.
Thank you so much for letting me record this.
Of course, yeah. Whoever else needs it.
Amen. It makes a big difference
Yeah.
to be able to see these things talked out slowly.